All right, we have a couple different ways of writing derivatives. There were some different. Newton had his way of writing derivatives. Leibniz had his way. Euler came up with his own notation, which we'll look at in more detail. But in general, if I have the function f of x, and I'm also going to say it's y, we can talk about the first derivative of being f prime of x or y prime of x. We tend, a lot of the times, to not write the of x for y and just write y prime. They say this is abusive notation, but what it implies is this is the dependent variable primed by whatever the independent variable is. And Leibniz notation was dy dx, where we can think of d as the change in y and this is the change in x, which helps with our definition of what the derivative ended up being, because the change in y over the change in x, it represents the slope of f of x, right? Or y. And so this notation, and we'll find that mathematically this can be useful for us, but mathematicians being lazy like writing these a lot. And so our second derivative is double prime and notice where the order 2 changes its location depending on what is the dependent and the independent variable. Our third derivative our fourth derivative, and notice how I've switched to a Roman numeral notation, and so on. We can continually take derivatives as long as we have an independent variable. Eventually we hit a constant in 0 and we're done. We get 0 as your derivatives further on down. Now, Euler would also use derivatives as an operator, and so you could do a d as a derivative operator, second derivative, and third derivative as an operator. And thinking of the derivative as an operator will be useful for us later on. And Newton, a lot of times in dynamical systems, if we, let's say we're talking about the position of a particle, and that particle is under a motion in time, we would think about x as a function of t. And so the derivative in Newton's system, or mechanical systems, is x dot for the first derivative, x double dot for the second derivative. And usually dynamical systems only look this far, but you can continue to x triple dot for dx dt. When you see the dots, it's definitely changing within time. This is talking about a change within time. Now, multivariate functions are functions of multiple variables. And for right now, I'll use the three-dimensional in time. And so we could also say, u is equal to this function. We get u as well. And so u and f are the dependent variables. U or f are dependent. But it's dependent on the independent variables, and I'm just going to abbreviate IND, x, y, z, t. Right? Three-dimensional positions. X, y, and z. And we always remember you want to keep a right hand rule. So if you were to take your right hand, let me try to see if I can do this without going. I'm going to try to use the camera. We'll see if it works well here. So if you take your right hand and you look at the x-axis and you rotate, this camera's in the right place, and I rotate to the y-axis, my thumb points to the z-axis. If I go from the y-axis and rotate to the z-axis, my thumb points to the x. If I go from the z to x, it points to the y. It's the right-hand rule. And if you looked at linear algebra, we have permutations that happen when we deal with axes, right? Z, I, J, K, right? When I, J, and K are permutations. to like this, it produces a positive 1. And if the order is out, let's say 3, 2, 1, 2, 1, 3, 1, 3, 2, it produces a negative 1. And that deals with how the normal vector points to the rotation on the plane. And so this this function, the EIJK function, can tell you, if this is x, y, and z, it points positively. And a right-handed system is positive. It's positive. And a left-handed system, these flip. If I do a left-handed system, these flip. And there are some times when you want a left-handed system, especially if your rotations are clockwise versus counterclockwise. And it's to keep track of the signs that we need when doing multivariate things. But this is our 3-dimensional system, and this one, well, 4-dimensional, it's dependent on time. And so we can talk about functions that deal with things on multivariables. But we can also talk about their derivatives. But change happens 3-dimensionally with respect to, I'm sorry, I'm flipping my notes here. We can think about change with respect to the x-axis. And notice we get a lowercase scripted d for, it's not this delta, it's a d, and this is a partial. And so the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z, the partial of f with respect to t. Or we could do the same thing with u. And these are first derivatives down one direction. It shows you the change in one direction. And I think for me, when I used to see partial derivatives when I was doing my Calc 3, kind of imagined I was on a slope. And if I was standing here and that was my z direction, how was I going down in the z direction? How was I going down in the y direction? Well, the vector that comes out of that we call the gradient. And so I always kind of imagined contour maps as I was going up and down a hill, kind of helped me think, how much do I change in u, in x, how much do I change in y, how much do I change in z? And so when I visualize these multiple dimensional things, I tend to think in contour maps. But you can also take, we can also write them in a common notation for mathematicians, is to write the function with a subscript of what the partial is in. Well, you can also take a second derivative. So I can take the second derivative of the function with respect to x twice, which would be the same as fxx or uxx, the partial with respect to this. Or I could take the second partial of f with respect to x and with respect to y. And dimensionally, these are the same. And so with multivariate functions, the derivatives can represent some very complex things. Well, that comes back into really, we have these ways of doing derivatives, and if differential equations have derivatives in them, what's the difference between, why are we studying ordinary ones? So let me clear the blackboard here, and I'll talk about the difference between ordinary and partial differential equations. And so there are two forms of derivatives, the multivariate ones, which are called partial derivatives, and then irregular derivatives, which you're going to call ordinary. So ordinary differential equations or ODE involve an unknown function and its derivatives in one variable. And so a common ordinary differential equation we'll see is like this. ordinary differentials. And I guess we could write this as x double prime plus b x prime. And what other notation can we use? These are all the same thing with different derivative notation across. And partial differential equations are differential equations involve partial, which I'm going to just PDE, partial differential equations, ODE, ordinary, involve an unknown function and its derivatives. Glad I'm speaking these words because my handwriting is going to pot on this right now. I also think I need to put a new battery in my pen. An unknown function and its derivatives. An unknown, should say, I'll just put down here an unknown multivariate function. The fun stuff. And so differential equations talk about, let me show you a partial. I think the wave equation would be a good thing to show here. So the second derivative of u with respect to time is equal to the equation constant alpha squared u with respect to position. And so how a function changes in time is equal to some squared function with how it changes in position. And this usually tells you the speed of sound. In the medium of the wave equation, in this the solution medium, this is the wave equation, and it shows us waves. Well, we are going to talk about ODE primarily in this course, and a general form for ordinary differential equations is some function equals 0. And so we have some function and all of the variables we can put into it, which is our unknown function and its derivatives, equal to 0. And the thing to know is n, where the highest derivative is called its order. So the order of a differential equation is the value of its highest derivative. And that's true for both PDE and ODE. I'm just going to show the ODE for the example. And if we go back to the two differential equations I showed before, this is a second order differential equation. So this is a second order ODE. And this also is a second order PDE. And then these differential equations can be linear or nonlinear. And we will really develop the idea of what is the usefulness of linearity, how linearity works on operators coming across into them. But the general form of a linear differential equation is one that's defined by a linear polynomial. So it's defined by a linear polynomial in the unknown function and its derivatives. It also means derivatives. You know what? For derivatives, I'm just going to put D or V right now. So we have polynomial that's linear. So we have the order of it, and this can be some function in x. It's okay that x is in here, and x can have any powers or anything as long as the unknown function only appears in its derivatives. Oh, and these are always functions of x. My apology for missing that one there. And this can all be equal to some function in x. And so you will never see a y squared or a dy dx to the fifth power, right? If this is linear, remember your linear functions all had powers of 1. And so the part that contains the unknown function, you won't see powers in it. Your y on its own here is to the first power, and any of its derivatives are to the first power. And so we can classify ordinary differential equations. Now, nonlinear differential equations have many different forms. Nonlinear have different forms. But the linearity of linear ones brings solution techniques and an algebra that will be useful, and it will help us in finding nonlinear. So most of the real world is nonlinear. Real world nonlinear. Our best tools are linear. And a lot of our job is going to be working on mapping between these two things. Because linear solutions are holonomic functions, are solutions, so let's just say f of x is some solution to an ODE. It's stable under addition, subtraction, sums, products, other differential equations, and integration. And so these operations that we've done, adding, multiplying, differentiation, and integration, these solutions to linears will work with this, and that lets us extend them. Nonlinear doesn't have that. And so we have to kind of use these tools to plug back into nonlinear. And most of the job of this course will be figuring out linear differential equations that we can find solutions to, and in some cases then applying that to the nonlinear. All right, what I'm going to do is I'm going to stop here, and I'm going to just show some examples of finding out the type of differential equations, and then we're going to look at some early models.